Hi, everybody. My name is Felipe. I'm very nervous to be here and speak in English, and it's Friday the 13th. Brazilians are very, very superstitious. But if by any reason I faint or I run away, my boss is right here, and he knows everything. He should just pick it up, and he can talk about this. I've been collecting how people describe what I do during this conference. And these are all titles that people gave me. Well, this is the one that I actually gave me. I'm a physical oceanographer. But some call me a data plumber, a cold janitor, a CI babysitter, or the Amazon dash button for Condoforge. That one I heard yesterday. So this talk is not new. There are many, we've been talking about this for a while here at SciPy. All talks delivered by great Rich Signell right here. There was this one on standards that we are using, and another one on how we use that standards to assess ocean models, for example. There is kind of a symmetry here because he was always speaking and he was showing my notebooks. Now I'm speaking, but I'm going to show his notebooks. So just before we actually dive into the talk, I would like to introduce what is I use. Micah is over here. Yeah, he's over there. So if you have a use question, you can ask him because I'm just going to glance it over. I use the Integrated Ocean Observer System. It's actually a community where we try to set up all these standards and a way to make the data go from the data provider to everybody. We have like a lot of records for our gliders, HF graders, ocean models. There is even animal telemetry. Who was here on the first lightning talk where Alex showed the animal telemetry network? That was pretty cool. We also have a code gallery where we demonstrate how to use all these services and data. So I invite you guys to visit this. It's all open. It's all copy and pastable examples. In fact, this presentation is a little bit of that. So what are these standards I'm talking about? We try to follow international standards, the Open Geospatial Consortium, ISO, and what Unidata kind of dictate us to use. And what we get from that, we try to avoid customer-specific solutions. We try to implement these standardizations at the data provider, so the lowest level possible. And the model is pretty simple. People run numerical models, they collect observations, the data provider apply these standards, and they serve the data via web services. And the end user is happy. What are these web services? Depending on your data type, it can be the Sensor Observation System, SOS. It's an Open Geospatial Consortium. We usually use that for buoys, stations, like time series. For gridded data, we use OpenDAP. Who here is familiar with OpenDAP? Almost everybody. And gridded satellites. And for raster image, we use WMS, which is also an Open Geospatial Consortium standard. It's the web mapping service. But lately, the community is converging to use ERDAP. Who here heard about ERDAP before? Not so much as OpenDAP. So ERDAP is something that I wasn't sold at first. I didn't like it. And after Rich bang on my head all the time, you have to use ERDAP, I kind of fell in love for it. I'm going to talk more about it later. But it's not there is a reason why the community is converging around it. It's pretty good. So the Sensor Observation Service, what is that? Pretty much like all the Open Geospatial Consortium standards, they have a get capability to get the metadata, a describe sensor to describe the instruments, and what we really want, the get observation to get the data. This is a typical URL for an SOS service, but if we add Python to it, it's prettier to look at, especially if Python 3.6 F strings. So one can envision on how to create a service or an app where we just populate those variables with Python, and you get, for example, a website where you can just click on the station and see a time series. Matthias Busonio said that I should trademark Jupyter time because no one used that before. So it's Jupyter time. So this is a typical example of how to access an SOS service. I specify a buoy, and I just throw that URL on a pandas, read CSV, and voila, I get the data. It's that simple. This particular station is here, Texas, and we can see a nice diurnal cycle for the tides. The URL also has latitude and longitude, so putting it on a map, it's Galveston area. I'm not really familiar with that region, but I think it's nearby. So the other service is OpenDAP, and OpenDAP is kind of tied to the hip to the Climate and Forecast Convention, which also allow us to read data in a standardized way. This is a typical CF metadata where you have the variable, the dimensions, a standard name, units, the coordinates where that variable is defined. Here we also have the non-dimensional vertical coordinate, which is usually painful to convert to a dimension vertical coordinate, but CF has all the instructions there to do it. When it comes to CF, oh, it's Jupyter time again. Sorry, that was quick. So usually when you come to read CF conventions, I use Iris. And the reason for that is that even though X-ray is great, X-ray doesn't do CF really well. I always say this, the best thing about Iris is that it's a CF model. The worst thing about Iris is that it's a CF model. So you had all these warnings when your data is not really compliant, or sometimes it even doesn't load the data at all. It needs to be real CF. But if it is, you get a nice representation of all the metadata and everything that's in there, including you get for free the derived vertical coordinate, which most clients won't do that for you. You need to compute that yourself. It's easy to plot and inspect the data. And again, you have the vertical coordinate there. So the third one was the WebMap service. It's kind of a simple HTTP interface to get georegister data. Like the OGC, you have the get metadata, the get sensors, or in this case it doesn't have sensors, but in the get data. You can serve JPEGs, PNG, DOTIFFs, and a typical WMS URL looks like this. Oh, sorry. This is the URL. In this case, I'm using some advanced search, like the time interval and the color range. And that gives me a really nice map where I can have a time slider and I can actually tune in what I want to show there. This one, I didn't use text, as I use my favorite oceanographic feature, which is the Brazil Malvinas current. I always find it beautiful to stare at. It's soothing, and I need that because I'm very nervous. So AirDAP. AirDAP is kind of the new kid on the block, and all the communities kind of converge around it. The good thing about AirDAP is all these different services that I talked about, you can have in there. You can have raster images, you can have time series, you can have models. But the best thing is that it's very flexible. So the responses are multiple. You can have an HTML table, the ARIS Esri ask and comma separated file, Google Earth KML, even the OpenDAP, and that's how I started it because I was kind of addicted to OpenDAP. I only knew how to do OpenDAP, so I started using AirDAP via OpenDAP. You can have MATLAB files because we play nice with our neighbors, NetCDF, the ODV text format, comma separated files, step separated files, JSON, etc. So all this flexibility is the reason why the community is converging around it. It has a really nice RESTful API. So everybody here saw Christian Fink talks on the website that they did. That was really great, but there was a lot of work there that could be just outsourced to an AirDAP server, especially because it standardized the time, coordinate, and it has a server-side searching and slicing. So you don't really send a lot of data back and forth. You request, I want this time at this region. The slicing happens at the server, and you get an image or the data in any of those formats. Jupyter time. So Matthias promised to be here and say that with me, but I guess he's busy somewhere else. So here's a typical AirDAP server. Here I'm using an AirDAP client. By calling this an AirDAP client is actually an overstatement because of this RESTful API. It's just a URL builder. And we just fill in with the queries that we want. Like I want that regional, that bounding box. It's the Gulf of Mexico, if I'm not mistaken. I want seawater temperature, and I want from the beginning of the year up to today, and I want trajectory profiles, basically because I'm looking for gliders. And I have the search interface, which is really nice because it gives me all the data set IDs available. So now I pick up one of those data set IDs, and I request the variables for that data set ID, and I get a download URL. In this case, I requested specifically the MATLAB, just to show that it does work. But they have some convenience methods like two pandas, where I just get the comma-separated file directly into a panda data frame. That's usually quicker and faster for us. And there's the data. So it's very convenient, very easy to use. And here's the latitude of that data. So yeah, I think Galveston is around here. So this gliding was navigating here in the Gulf of Mexico. So yeah, but if you see there is a pattern. At first on SOS, I had to hard code my stations, and then on the OpenDAP, I had to hard code my endpoint. With AirDAP, I actually didn't hard code the data set ID or anything, but I still had one server hard coded for the server. There are many moving parts there. So how do I navigate all this? The catalog. That's actually the meat of this talk. So I use this geo catalog. That's a single source to find all these endpoints. There is a nice Python interface via the OWS lib catalog service web. We can do advanced filtering, use FAS, and it's not like OpenSearch. Like we can create very complex filters with ORs, NOT, and things like that. And it's really the one thing to rule them all, like find all these services in a single interface. How does the catalog work? We have this register table with all the endpoints that we want to carry. It can be threads, SOS, AirDAP, or WAF endpoints. They are harvested nightly. They are transformed into ISO URLs. So again, an international standard. We didn't come up with anything new. We're just adopting what the community is using out there. We publish that to the IU's regional WAFs. We synchronize to the DO portal, and we have the catalog. So how do we navigate the catalog afterwards? We need to sniff those URLs. There is a Python library for that that's called geolinks, where once we find an endpoint, we ask, what kind of endpoint is this? Is this an SOS? Is this OpenDAP, WMS, or AirDAP, or whatever? I mean, they have some that we don't really use that much, like KML or, well, KMZ, KML are the same type of service. Just one is zipped and the other one's not. Jupyter time. So how do we query the catalog? It's relatively similar to how we query the AirDAP server. We have a bounding box. We have a time frame. But here, I can actually use many variables. In this case, I have all the CF name, the climate and forecast names for temperature. And then we create a filter like this, where basically I say, hey, I want and that bounding box at the beginning and end, or one of these properties here, that's those that are in the CF variable names, and I don't want anything that has the string CDIP. So we can construct very complex filters to get only the data that we want. And then again, using OWS lib, we found 127 records for the Gulf of Mexico. Here are all the records. I'm not going through all of them, but virtually all the buoys that we have here, we found. Oddly, I didn't find any models, Rob. Where are your models? Sorry. So we can go over the metadata to investigate more about what we find and what kind of variables are available. We can sniff the links and see the services, like they're usually all SOS services, but I think I found some OpenDAP services. And it's really nice because you can even find direct links, like this is a link for technical report manual. It's in there in the catalog if you want to read it. And again, we can just download the data very easily. I got actually the same buoy from the first plot where I hard-coded the buoy, but in this case, I found that buoy automatically using the catalog. There I plot sea level surface, and here I plotted the temperature. But the title of the talk is how to build your own app. And now I'm talking about is standards, and how to use those standards. So now let's go to a real example where we tied all the services together to do something really cool. So this one is not actually a presentation. It's just a notebook that I'm going to go over relatively quickly. This one, we hard code a hurricane code from the National Hurricane Center. And this is the only thing that the user needs to set. After this, it will download all the shape files for the cone prediction of the notebook for the hurricane. And based on the latitude and longitude and time span that found on that shape file, it will query those services and get all the data available for that region and that time. So basically, there's a lot of boilerplate code here to download the files and to create the filter, but the user doesn't really need to know about all that. He only changed the hurricane code. We found all these stations. I single out one plot here just because it's a curious plot, because we get the eye of the hurricane where the wind speed went really down and we had the sea level surface at the maximum. But then we put this all together in a really nice map like this one, where we have a WMS sea surface temperature on the background. We have all the cones predictions. We have the status of the hurricane in each point. And if we zoom in, we have bokeh plots showing all the stations that we found. Everything happened automatically, just based on the hurricane code.
That's so rad, dude.
It's not the best one. There's two more. Wait, there's more. This one, actually, this one, we Signell showed a version of it some years ago where we did a numerical model assessment for temperature in, I think it was Massachusetts Bay, right? This one does a similar thing, but it's wave height assessment. And this is how easy to switch applications. Like in his case, he had temperature variables here. I just switched it to wave variables. I tweaked the dates a little bit, and that's it. I just rerun it, and now I have virtually the same notebook, but instead of comparing observations of temperatures and model temperatures, I'm comparing observation of waves and model waves. All the models are found automatically, are plotted automatically, and all the stations are matched to those models automatically. The only thing that the user changed is this cell right over here, where we declare the dates, the variables of interest, and the catalog. And there is a nice trick here where we standardize the units as well. So I want everything to be in meters. So if we find something that's in feet or centimeters, it will convert to meters, so we can actually compare on the plots. But that's not the best one. The best one is this one, because it's the actual title of the talk, how to create your own app using all the services. So thanks to Binder, one can create a notebook in app mode. In this case, we're using the AirDApp RESTful interface to do this. And you can fool people to think that this is an actual app, while it's not. It's just Jupyter widgets where someone can click here and have an updated plot of that specific station. You can change the variable of interest here. In this case, I'm change to seawater salinity, and which is going to be mad at me because I didn't fix here this. When you have more than one sensor, it will plot all the sensors together. But it's pretty easy to fix. You can create multiple subplots in there. But if someone doesn't know that this is a Jupyter widget, they're going to think that this is a professional dash app that someone cooked up, like Christian Fing's website. Of course, sometimes you don't want this. This is almost like a play toy, but you can use your app for professional websites. And this is a really nice example. It's the Secura portal. Secura is one of the regional associations for IUs, where basically they access all the data that's available using AirDApp, RESTful APIs, and the server-side license to create multiple kinds of visualizations for models, buoys, gliders, and whatever data is in there. So in summary, all these standards and web service in the catalog help us to serve the data in a unified way. Python and Jupyter is a very powerful tool for us to visualize and explore and fetch this data. And widgets allow us for fancy visualization and exploration. So that's what I had for you guys. Hope you enjoyed it. And if you have any questions, I'm happy to take them. And if you want to play with this, just click on the Binder link. I'm going to tweet the slides and all the links for all the notebooks.
Questions? Got to be a few at least. That was incredibly cool. So is the general idea that people would kind of wrap their own stuff around this or kind of set up their own portal?
That's the general idea. Yeah,
Okay.
you can create your own portal, like with your own branding, your own kind of bots.
Are you guys open to people like just kind of using your portal for that as well?
As well, yeah.
Okay, great. I have some projects in mind already.
And it's not only oceanographic data. I mean, I'm a physical oceanographer, so I was biased here, but there is way more data in there.
Okay, how about like weather and
I'm pretty sure there is all the weather stations and everything. Yeah.
Nice.
I just don't care about them. Sorry, Ryan.
That was great. So could you make like a simple Flask app that does all that and then spits out the iframe with your Folium plot?
You could. I actually did that. I recommend trying Dash. It's a little bit better than Flask, but yeah, at the end of the day, it doesn't matter which web framework you're going to use, because it's just RESTful APIs, and I also recommend SciPy leaflets, not Folium, because Folium is dying. Sorry.
More questions?
Actually, I just was wondering, is AirDAP, is that developed by the core engineer? I mean, or why?
Do you want to take that one, Rich?
It was developed by the NOAA Fisheries Service,
Oh, okay.
but it's open source, and it's completely flexible. Any kind of tabular data, doesn't even have to be geographic data, but all those services become available. It's really easy. It's pretty easy to install. The instructions are really good. If you want to run your own server, it's really easy.
Yeah, they're serving even sound now, because some of the biologists, they need whale sounds for some reason, and there is even sound.
We have time for one more if anyone wants.
Is the seismology data like a data sets available for?
I don't know. I'm not sure. If Mike Heaney is here, and there he is, do you want to take that
Not
one?
for AirDAP that I'm aware of, but you could probably import it.
Yeah, you could probably put it in there, I'm pretty sure.
Okay, let's thank our speaker again.